All right. So the next thing I want to talk about with probability theory is about complements and unions of events. So we'll start with complements first. And again, our knowledge of set theories is going to come in handy here, right? So you may recall that if E is an event, then its complement, which we denote with that little apostrophe, E complement, is everything in the universal set that's not in E. And so the picture that we had for that was this, right? So you have your universal set here, which now we're just thinking of that as the sample space S, okay? And then you have some event inside of your sample space that we'll call E. And then everything else that's in the sample space but that's not in E is E complement, right? E complement is all of this stuff out here. All right, so that's E complement. One thing to point out here that should be pretty obvious is that any outcome in a sample space is either in E or it's in E complement, right? It's either inside of the circle or it's not inside of the circle, right? So any outcome in the sample space is either in E or it's in E complement. And so what that means is that if you look at the probability that E occurs, and then you look at the probability that E complement occurs, well, if E does not occur, then E complement does occur. And if E complement does not occur, then E does occur, right? So if you add the probability of E to the probability of E complement, you should get 1, right? It's 100%. You're 100% certain that either E will happen or it won't happen, right? So probability of E plus probability of E complement is 1. Now, if we want to solve for the probability of E complement, we would subtract probability of E from both sides of this equation, and we would see that probability of E complement is 1 minus the probability of E. So here's another picture, right? So the rectangle represents our sample space S. E complement is all of this stuff out here. E is all of this stuff in here. And E has probability P of E. E complement has probability 1 minus P of E. All right. Now, I don't know why, but this concept in my experience causes students a lot of confusion, okay? But it really shouldn't cause you any confusion. So let me give you an example to hopefully make it crystal clear, right, what it is that we're talking about. So, for example, if 25% of people own a dog, what's the probability that a person does not own a dog? Right? In other words, we could say probability of D for dog, right? So probability that they own a dog is 0.25, right? Because 25% is 0.25. So we're told that probability they own a dog is 0.25. And the question is, what's the probability that they don't own a dog, right? What's the probability of dog complement? Well, according to the formula up here, right, probability of dog complement would just be 1 minus the probability of dog, right? So probability of D complement is 1 minus probability of D. And we know that probability of D is 0.25. So probability of D complement is 1 minus 0.25. And what's 1 minus 0.25? Well, it's 0.75. You can use your calculator if you need to, right? But probability of D complement is 0.75. So there you go. If you want to change that into a percentage, you can. 0.25 is 75%, right? So now think about that, because it's just common sense, isn't it? If 25% of people own a dog, then 75% of people don't own a dog, right? So it's just common sense. And so that's why I say this thing sometimes causes students confusion, but it really shouldn't. It's really just common sense. And this is a good example to keep in your mind. If you're trying to remember, what's the complement rule? What's the complement rule? Just remember, if 25% of people own a dog, then 75% of people do not own a dog, right? That's all the complement rule is really saying. Let's practice applying it to some different situations. So this first one says, the accompanying graph shows how a group of first-time voters are classified according to their party affiliation. If we randomly select a person from this group, what is the probability that the person has a party affiliation? Well, what is that supposed to mean? Didn't they just say that they were organized by party affiliation? So maybe we should look at the graph and try to make sense of what they're saying. So this blue represents Democratic. So we've got 37.1% of voters, first-time voters are Democrats. And then 24.1% of them are Republicans. But then look at this orange one, right? What does orange represent? 23.7% of people are in the orange category, but what's the orange category? It's none. Okay, it's none. So these are the people who are unaffiliated, right? They don't have a party affiliation. So 23.7% of people don't have a party affiliation. So now let's read the question again. If we randomly select a person from this group, what is the probability that the person has a party affiliation? Well, we know that 23.7% of people don't have a party affiliation. So by the complement rule, it should be the case that 100% minus 23.7% of people do have a party affiliation, right? So note, so we'll say probability, how should we say this? I'll say A means has a party affiliation. Okay, so A for affiliation, right? So note then that probability that they do not have a party affiliation, so probability of A complement is 0.237, right? 23.7%, right? It's 23.7%. And you can just you can see that in the pie graph here. We're being asked, what's the probability that the person has a party affiliation? So we want probability that they have a party affiliation. We want P of A, not P of A complement. Well, according to the complement rule, well, actually, what the complement rule says is that probability of A complement is 1 minus probability of A. But it came from this statement, right? That probability of E plus probability of E complement equals 1. So we could also solve for probability of E by subtracting probability of E complement on the other side. And then we would get probability of E is 1 minus probability of E complement. So they have this very symmetric relationship, okay? So probability of A is 1 minus probability of A complement. So that's going to be 1 minus 0.237, which if you punch that into your calculator, 1 minus 0.237 is 0.763. 0.763. Okay. Now, that's just one way to do the problem. There are other ways that you could think about this, right? Because we're being asked, what's the probability that the person has a party affiliation? Well, it should be the case that when you add up the Democrats plus the Republicans plus the Greens plus the Libertarians plus the others, that you should end up with the total number of people who have some kind of party affiliation, right? And so the only category we're going to leave out are the people who said they don't have a party affiliation, right? So we could just add up all those other numbers. So I'm not going to do 23.7, but I'm going to do everything else. All right, 7.2 plus 3.5 plus 4.4 plus 24.1 plus 37.1 equals, and what do you know, right? 76.3%. The same answer as what we got before using the complement rule. The complement rule is much quicker though, because instead of having to add up 1, 2, 3, 4, 5 numbers, we only have to subtract 2 numbers, 1 minus that. Right? So the complement rule can save us some time if we can recognize that it's usable in certain situations. Okay, let's look at another one. Or actually, we're going to move on. All right, so complement rule is not terribly complicated, and hopefully, you have some intuitive understanding of it. What I want to look at next is the union of two events, right? How to compute the probability of a union of two events. Well, so first of all, recall from set theory that E union F is the set of all elements in E or F or both. And here's the picture. Here's the Venn diagram, which a couple of you said on your test too that you don't like the Venn diagrams. So I apologize. But anyway, if this is E and this is F, then E union F is all of this stuff, right? It's everything in E or F or both, right? Both is the overlap part, but it's everything in E or F or both. And again, this entire rectangle represents the sample space. Okay? So, if we want to find the probability that some event E or some other event F occurs, then we would compute probability of E union F. So really the point I'm trying to drive at is that the union symbol means or. You should think, when you see the word or, you should think union, right? Union. In the next section, we're going to talk about intersections. And intersections correspond to and, right? And means intersection. Okay? But that'll be in the next section when we talk about that. All right? Although this will come up a little bit in this section as well. Okay? But anyway, so if you want to find the probability of E or F, then you're going to compute the probability of E union F. And that's going to be the cardinal number of E union F divided by the cardinal number of S. Or, in other words, it would be the number of ways that either E or F or both could occur, divided by the total number of possibilities. Okay. Now, when we were doing set theory, one of the things that we discussed, I think it was probably a homework problem, was that if we want to find the cardinal number of E union F, we have to be careful that we're not double counting whatever is in the intersection. Okay? So one way to do this would be to count the cardinal number of E, and then count the cardinal number of F, and then add them up, but then subtract off what they had in common because, we've double counted it. So, in other words, what I'm saying is this. Let's say that E has like 10 things in it, 10 elements. And let's say that F has like 15 elements, but they share 5 elements in common. So if you say the number of elements in E union F is 10 plus 15, well, you're going to be wrong, right? Because you double counted the 5 here. You counted the 5 here when you counted the 10 things that were in E, and then you counted them again when you counted the 15 things in F. So in order to undo the double counting, you need to subtract off this middle part. So you would say it's 10 plus 15 minus 5. Okay, so that you're not double counting what's there in the middle. And that's exactly how we end up with the following formula for the probability of E union F. So if E and F are two events, then the probability of E union F is the probability of E plus the probability of F minus the probability of E intersect F. Or in other words, you could read it like this. The probability of E or F is the probability of E plus the probability of F minus the probability of E and F. Now, if E and F have no outcomes in common, then we call those mutually exclusive events. And in this case, the intersection of E and F would be empty because they don't have anything in common. And so the probability of E and F would be 0, right? And so this formula would just simplify down to this. My advice would be ignore this thing, right? A lot of times students want to jump straight to this formula, but you can only use this formula if you know that E and F are mutually exclusive. Otherwise, you should use this formula. And the nice thing about using this formula is that if E and F happen to be mutually exclusive, this is going to go away anyway. So you're going to get the answer right if you use this formula every single time. If you use this formula every single time, sometimes you'll be right, but most often you'll be wrong. Okay? So use the top formula, right? Make sure to subtract off whatever the events have in common. So here's a picture, right? We've got our sample space S, we've got E, we've got F. The union of E and F is everything within these two bubbles. And where the two events intersect, the outcomes contribute twice to the probability of E union F, so you have to subtract off a copy so that you're not double counting. Let me give you an example. This one says, suppose that the probability that you get an A in math is 0.8, the probability that you make the dean's list is 0.72, and the probability that you both get an A in math and make the dean's list is 0.6. What is the probability that you get an A in math or make the dean's list? Okay, so here's what I'm going to do. I'm going to try to translate some of these sentences into some probability notation because it's going to make things easier, right? So the first statement says, suppose that the probability that you get an A in math is 0.8. So I'm going to call that M, right? Probability that M for math, M for math. So probability you get an A in math is 0.8, right? That's what that first statement says. The next statement says the probability that you make the dean's list is 0.72. So probability you make the dean's list is 0.72. I'm going to call that P of D, right? D for dean's list, 0.72. Okay. Whoops. Sorry about that. Okay. And then the next statement says the probability that you get both an A in math and make the dean's list is 0.6. So the probability that you get both an A in math and make the dean's list is 0.6. So that I'm going to call the probability you get an A in math and that you make the dean's list is 0.6. Remember the and means intersection, so this is probability of M intersect D. Okay? And then we're asked, what's the probability that you get an A in math or make the dean's list? So we want to find out what's the probability that you get an A in math or that you make the dean's list. In other words, we want the probability of M union D. Well, according to this formula up here, that should be probability of M plus probability of D minus the probability of M intersect D, right? So that's 0.8 plus 0.72 minus 0.6. Okay, punch that into your calculator and see what you get. So I get 0.92. Okay. All right. So that's that one. Well, let's look at some more. So here we've got our standard deck of cards again. It says, if we select a single card from a standard 52 card deck, what is the probability that we draw either a heart or a face card? Okay. So either a heart or a face card. Well, so we want probability that we draw a heart or a face card. That's going to be the probability that we draw a heart plus the probability that we draw a face card minus the probability that we draw a heart and a face card. Okay? Well, what's the probability that we draw a heart? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hearts out of 52 cards in total. So that's the probability that we draw a heart. What's the probability that we draw a face card? Remember, our face cards are the jack, queens, and kings. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 out of 52. And then probability of H intersect F. H intersect F, this would be hearts intersect face cards. So in other words, these would be face cards that are hearts, or hearts that are face cards, however you prefer to think about it. There are 3 of those, right? The Jack of Hearts, the Queen of Hearts, and the King of Hearts, right? So those 3 cards satisfy both conditions. They're hearts, but they're also face cards, right? These ones are face cards, but they're not hearts. Face cards, but not hearts. Face cards, but not hearts. And these are hearts, but not face cards. So the only cards that are both hearts and face cards are Jack of Hearts, Queen of Hearts, and King of Hearts. So 3 of them out of 52. Okay, so what does that come out to? That comes out to 13 plus 12 is 25, minus 3 is 22. So 22 out of 52. You can change that into a decimal if you want, but I'm going to leave it that way because I want to show you that you could have just counted this up differently. Because this is actually a really good example that shows why this formula works, right? Because if you just count up the number of cards that are hearts, you get 13. And then if you count up the number of cards that are face cards, you get 12. But then you've double counted these 3 cards, right? You counted them once when you counted the hearts, and then you counted them again when you counted the face cards. And since you double counted them, you need to subtract off those 3 so that you're really only counting them once. Well, so another way that you could do the same thing would be to just count like this. You could say, well, hearts, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then face cards, well, I've already counted those 3, so I have 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Right? So 22 out of 52. Okay? So that's that one. Let's move on to the next one. It says, the following table represents the number of active duty military personnel by rank in the 4 major branches of the military as of December 31st, 2007. If an active duty member of the military is selected at random, let's maybe spend some time looking at this chart, right? So this is actually pretty far out of date, right? But anyway, so we have officers here, enlisted personnel here, and then totals. And then here we have the branches of the military: Army, Navy, Air Force, Marines, and then totals, right? So the total number of officers is 220,506. The total number of people in the Air Force is 325,725. The total number of people in the military, period, is 1,355,137. Okay? The number of enlisted Navy personnel, 278,193. So hopefully you understand how the chart is organized, right? So it says, if an active duty member of the military selected at random, what's the probability the individual is an officer? So the probability the individual is an officer, I'm going to say O for officer. Well, there are 220,506 officers in total, out of 1,355,137 military personnel in total, right? So probability that you randomly select an officer would be 220,506 out of 1,355,137. And let's change that into a decimal. So that comes out to about 0.162, I'll round that one to 0.163, right? It's 162718, blah, blah, blah. So if I round to 3 decimal places, the next number is a 7, which is bigger than 5. So I have to bump that up to a 3.163. Oh, that's ugly. 0.163. Okay. What's the probability the individual is in the Navy? Well, in the Navy. Now be careful. You're not going to say 51,167 because those are just the naval officers, right? But we want the total number of people in the Navy, which is this number here, 329,360. So the probability that they're in the Navy is 329,360 out of 1,355,137. Which comes out to about 0.243. So I'm going to round all of these to three decimal places. So again, notice that third decimal place, the fourth one is a 0, which is less than 5. So I don't bump that one up, I just leave it a 3. Okay. Part C, what's the probability the individual is a naval officer? Ooh, a naval officer. If you're a naval officer, that means you have to be in the Navy and you have to be an officer, right? So this is really like the probability that you're an officer and that you're in the Navy. So officer and in the Navy, right? There's the intersection, right? Officer, Navy. So there's the intersection. Okay, so it's 51,167 out of 1,355,137. And that comes out to about 0.038. Okay. And then finally, what's the probability the individual is an officer or in the Navy? Officer or in the Navy. Well, that's the probability the individual is an officer plus the probability the individual is in the Navy minus the probability the individual is an officer and in the Navy. And wouldn't you know it, those just so happen to be the things that we calculated above. So I'm going to say this is approximately 0.163 plus 0.243 minus 0.038. And that comes out to 0.368. Okay. Now, you could also do this one differently. You could say, well, instead of using this formula, why don't I just look at the chart and figure it out? And you could say, So what's the probability the individual is an officer or in the Navy? So you could say, well, there were 220,506 officers, and then there were 278,193 Navy personnel who are not officers. So if I add those two numbers up, so if I add 220,506 plus 278,193, and then divide that by the total number of people, so divided by 1,355,137, you get 0.368. 0.368, right? Just like what we got when we used the formula. Okay, so you're welcome to use whatever method you like. I don't really care if you use the formula or not. I just have included it, to make it easier for you. If it doesn't make it easier for you, then by all means, don't use it. There are going to be some circumstances where I think you kind of have to use it, like the very first example we looked at down here, because you weren't given a chart with all of the information. You were only given certain pieces of the information, so you kind of had to use the formula. But here you don't have to use it if you don't like it. You could do it in the second way that I just showed you. All right? So it's up to you. Let me give you one more example. Ooh, okay. I'm giving myself a hint. Usually when I give myself a hint, it's because it's kind of a difficult problem. So hold on. Bear with me here. Let's read through this. It says a survey of 1,600 consumers compared the amount of time they spent shopping on the internet per month with their annual income. The results are in the table below. Okay. So this is the amount of time they spent shopping on the internet. So some people spent 10 hours or more shopping. Some people spent 3 to 9 hours shopping, and some people spent 0 to 2 hours shopping on the internet. And these are their income brackets. So if they made more than $60,000 a year, then this is the breakdown, right? 192 of them spent 10 hours, 176, 3 to 9, 128, 0 to 2, right? So this is their income brackets, $40,000 to $60,000, and then below $40,000. And then we have totals, right? Totals. And then the grand total here, 1,600 people. So let's see. It says, if we select a consumer randomly, what is the probability that the consumer neither shops on the internet 10 hours or more per month, nor has an annual income above $60,000? The hint I'm giving myself is that this is the complement of a union. Yeah, it is, right? It is the complement of a union. The union in question is the union of people who shop on the internet for 10 or more hours per month and people who have an income of more than $60,000 a year, right? We want the complement of that. So, right, we don't want the person to be in this column, and we don't want the person to be in this row, because we don't want them. It says, what's the probability the consumer neither shops on the internet 10 hours or more per month, so we don't want that, nor has an annual income above $60,000, so we don't want that, right? So one thing that we could do would be to actually find what's the probability that their 10 or more union above 60,000, and then take the complement of that, right? So in other words, I'm thinking like this. We want the probability of, what should we call this? 10 plus hours. So I'll just call it 10 plus. We want the probability that they shop 10 or more hours per week. Union, the probability that they make 60,000 or more. Complement, right? We want the probability of the complement of that union. So first I'm going to find the probability of the complement, or probability of the event itself, right? So I'm going to say, what's the probability that they shop 10 or more hours per week, union, that they make 60,000 or more per year? Well, that's going to be the probability that they shop 10 or more hours per week, plus the probability that they make 60,000 or more per year, minus the probability that they shop 10 or more hours per week and that they make 60,000 or more per year. Well, probability they shop 10 or more hours per week. There were 480 people who did that out of 1,600. Probability that they make $60,000 or more. 496 people made $60,000 or more per year. And then probability of both. Well, there were 192 of those people who made above 60,000 per year and who shopped 10 or more hours on the internet. So we subtract those off because we double counted them, right? We double counted them with the 10 or more, or we counted them once with the 10 or more, and then we counted them again with the above 60,000. So we need to subtract them off so that they're not double represented. Okay, let's see what this is. 480 out of 1,600 plus 496 out of 1,600 minus 192 out of 1,600 is sorry, I'm going to change it into a decimal. So that comes out to exactly 0.49. Okay? So to interpret that, you could change that into a percentage and call it 49%, right? So we would say 49% of people either spent more than 10 hours shopping on the internet or made more than $60,000 per year. So now, if we want the probability that that a randomly selected person didn't shop more than 10 hours on the internet nor made more than $60,000 per year, we would use the complement rule, right? So we would say probability of 10 plus union 60,000 plus complement is 1 minus the probability of 10 plus union 60,000 plus, which is 1 minus 0.49, which is 0.51. So 51% of people neither shopped online for more than 10 hours nor made more than $60,000 per year. Okay, so that's that. Now, if that was all very confusing to you, I think there is a much easier way to do the problem. So I don't really like the hint that I gave myself because look, we don't want the person to be in this column. We don't want the person to be in this row. That means these are the only 4 options. So I think if we just add up 208, so I think if we add up 208 plus 144 plus 192 plus 272 and then divide by 1,600, sure enough, we get 51%, right? Same answer. Same answer as before. But anyway, but you could do it using a formula, using in this case, we're using 2 formulas. First, we used the union rule, and then we used the complement rule. So you could use them together to do all kinds of crazy stuff. But that's that. Okay, that's all for that section.